Oh, yeah, so I'm recording. But now I feel I've got some things to look at, and I'll tell you about those at the end if you're still with me. So this is where I started. Well, I have two different motivation strands, but I'll tell you how I started. I was interested in basically Einstein's dreams, that we have the field equations like general relativity, and the solutions to those also that have some particle-like solutions. And I know from this forum that's something would resonate with people. And you might hope that also that this would explain quantum theory for those people who think it is worth explaining. And obviously, none of this is of much value unless you are able to unify the forces of nature. And when I first started studying, everyone ignored gravity. That was the one you didn't bother with, and you tried to unify the others. Now it's the other way around, isn't it? Everything else sorted out, just left with gravity. And it's a very nice geometric, offers potentially a nice geometric interpretation for perhaps people who can't, stuck in their old ways, like me. In fact, it offers more than interpretation, because what we're talking about here is an explanation. This is something that can give results, derive results potentially, and make some predictions. I do make some predictions. Unfortunately, they're not particularly testable. So this is one of this is what Einstein was trying to do with he got general relativity, and then he was trying to look for particle-like solutions, and then he tried other variations or extensions of general relativity, and as always his test was to find a particle-like solution. And at the time when he was starting this, there was only the electron and the proton. So I mean, I don't think he was guided all that well by what to look for. But so this was one of his ideas for a particle picture. So this is a black hole, and in a sense, if you're living out in the universe around it, it looks like a massive object. You would assume from the gravitational field that there was a source of mass somewhere, but actually the equations do work with no source of mass, because you could have a throat to it connected to another wormhole in some other part of the universe, and this is a two-dimensional version of the universe, and this is just to show that this hole is to someone living in the universe is quite a long way away, but they're connected through this throat, and on this side it will also look like a mass. So this was a bit, it was saying something and offered some promise. It might have suggested that for every particle it was intrinsically linked to an antiparticle or something like that. It's a nice picture, right? And then Missler and Wheeler were doing something similar. Again, this is just another way of depicting the same thing. Two wormhole mouths, each of which looks like a particle. And what they've done with this, I talked about with this, is threading it with flux. So you can have electric or magnetic flux going through here and out the other one, and there is no source for this flux. There is no there's no actual charges, magnetic or otherwise. But if you look around this region and look into it, effectively, this is a charged particle. It has a mass, and it is essentially a source of the field. And for everyone here, there is an equal and opposite sink for the field. So the Einstein-Rosen bridge shows that there was mass without a source of mass. This shows not only is the mass without a source of mass, there are charges without a source for charge. Right. But when I started looking at this, clearly these models have got to give particle properties like charge and mass, and we just see now how they can have charge and mass, not necessarily quantized. And maybe some interactions. The field equations may show how they developed. But they've got to have particle-like behavior, or they're not particles, are they? And that means this is only going to work if they behave like quantum particles, which is something of a problem. So it's an old idea. Einstein and Rosen did that first one. Missler and Wheeler did quite a lot. They called it geometrodynamics. But it's got to agree with the predictions of quantum mechanics. Somehow it's got to be able to show the essence of quantum mechanics. where in fact it's got to show all the features of it. But yeah, and it's quite a radically different view of space and time and new predictions. But there is something that's required, because the old models had nothing to do with quantum theory. And here's a different motivation. So we have quantum theory, we have the theory, we have some experiments, and it's I've written contextual, haven't I? Yeah, it's contextual. It's a contextual theory. It's non-local. If we're going to give an explanation for it, somehow or other, we need to describe the present state with some knowledge of future experiments. And to me, I don't know whether you look at it quite this way, non-locality and contextuality are pretty much the same thing. If something's not non-local, you don't know what was cause and what was effect. You don't know which part of the experiment was done first. So the obvious question is, I mean, I don't know why people aren't just sitting back and thinking. So we got this strange quantum theory. We know it's right, but well, what's going on here? So you're going to look for an explanation. Well, where would you look? Well, let's look for your best theory of space and time. I mean, this is saying something about causality and the structure of space and time. So let's have a look at our theory of space and time. Let's find the best theory of space and time, see what we can say. But we only have one theory of space and time. It's general relativity. So we don't have to make many choices to know where to go, or at least where to go first. So this is my 2-minute introduction to general relativity. The important thing about this equation really sums it up. This is the Einstein tensor, which is dependent on the curvature. It doesn't have all the curvature information in, but it is a curvature tensor, and it's equal to the stress energy momentum tensor with some constants poking around somewhere. This G can be calculated just from the metric and its derivatives at a point x. Yeah. And now, at least, despite the maths looking rather horrid, particularly when it was introduced, it seems to be well accepted. It's understood. It's geometric, so it helps with an explanation. The equations are non-linear, so that gives a lot of scope for all sorts of things. It's worth emphasizing that these are local. I don't mean in a quantum sense. Equations, they're about x, and the derivatives are x. These equations can be evaluated point by point around the manifold. They might constrain the topology and vice versa, but they are by and large separate from it. So there's something to be added from this, yeah? And you can disassemble the equations, and if you have a space-like hypersurface with a certain curvature and derivatives and its energy momentum, you can, it's fully determined. Yeah? And what is known as a esoteric feature of this, it does allow closed time-like curves. There is nothing here that prescribes the causal structure. And if you have any doubts about that, you can just think of a flat space-time, and you can join t equals 10 years with t equals minus 10 years, and everything will go, the whole universe will keep going around in circles. That's all totally consistent with these equations. And there are a number of examples that are known about mathematically. Yeah. Yeah. But this is where I start getting interested. And this is then has some links with quantum theory, at least potentially. Because if you can have some interaction between the past and the present in closed-like terms, or some aspects of the acausal structure, then you're in a position where subsequent measurements, in principle, you need to know what they're going to be before you can solve the equation. In other words, the present state is dependent on future measurements. So yeah, initial conditions may actually depend on the setting of the measurement apparatus, and So it immediately becomes a non-local hidden variable theory, which we think we'd be looking for. And if that is so, it will result in the probability structure of the same probability structures as quantum theory. So what I'm saying is it could at least potentially explain quantum mechanics. And we can prove that in principle. Yeah. And in which case, quantum theory then becomes just a special case of general relativity. So we have classical general relativity, but when we have structures with acausal structures, they obey the rules of quantum theory, and the rest of the universe carries on classically, which isn't what many people are expecting the outcome to be. But if you remember that 90% of the universe is dark matter and doesn't seem to be interacting with us very much at all, maybe there's something in that as well. So these are the steps. If you have general relativity with closed time-like curves with a causal structure, then the questions, the experiments you can do will satisfy quantum logic. My first research paper was exactly that, showing how you could get quantum logic from general relativity by going through all the axioms of the quantum logic and showing how they were derived. But with hindsight, I could probably said it all in one sentence. It's intrinsically contextual when you've got closed time-like curves, and quantum logic is the logic for contextuality. If you have quantum logic, then you can show that that's a representation of that is Hilbert space. And that's done by, for example, Beltrametti and Casanelli and Rausch. And that's in the textbooks. And if you have a Hilbert space structure for your propositions, for your states, then you can show that you can derive Schrodinger's equation. Yeah, a constant comes in, which becomes Planck's constant, and that's done. Ballantyne does that really nicely, I think, for the non-relativistic case. Weinberg's book deals with it for the relativistic. And what was I going to say? Gleason's theorem tells you what the probability structure has to be on it. There's basically nothing else that can happen in this route. You can't end up anywhere else other than a non-trivial 0 equals 0 equation of motion. My maths supervisor sort of said, well, that's one of those horrible sort of proofs that's sort of right, but doesn't illuminate anything. It doesn't actually tell you what's going on. It just tells you it definitely has to be like this. So here you are. It definitely has to be like that. Now, there's a thing with the topology change. If I'm modeling particles with as these topological structures, then when there's an interaction, if they're coalescing or splitting up or something, there's a topology changing interaction taking place. But there are some constraints on that from the theorems, Jarok's the famous one, yeah? We need either of a number of conditions to be satisfied. Either singularities appear, which really is just another way of saying general relativity breaks down. You need closed-like times curves to start appearing somewhere, and that needs a negative energy source for their creation, which, well, you know, maybe there will be, maybe there won't be. But another one is a failure of time orientability, which is what I've latched on, which I find most interesting. I've got a little picture of it here. So this is a very simple topology change. It's an S1 plus S1 universe, particles, whatever, changing into a single S1. So they're coalescing, if in a sense. And down here, you can put a time direction everywhere. You can put one here. It's slightly complicated in mathematically because they're disjoint spaces, but we'll gloss over that for now. And you can have a, on this slice here, you can have a well-defined time direction, but actually to get from here to here, something has to go odd. I mean, so what seems to be a forward-going time direction back here is someone else's is a backward-facing arrow. So this is is not orientable anymore. You can't on this object consistently put a time direction. Right, so I'm now slightly going into time orientable. Is this something people are familiar with or not? Orientability or not? No one has anything to say. I will carry on as if you are not terribly confused, but might be like refreshing then.
Yeah, keep going.
Thank you. So most people with orientability might be thinking of a Mobius strip, and that's probably not a bad thing to have in your mind as I chat through this. It's certainly it's one of the very few objects I can visualize for this. In Minkowski space, so 3 plus 1 dimensional, space orientability and time orientability are separate properties, and you can have any combination. The general assumption is that space and time are both orientable, but you can have one or the other or both being not orientable. It must be because the full Lorentz group can be split into 4 different subgroups. I think I'm saying that right. The other thing about non-orientability, it's a global property. It's a property of the entire manifold. If you do a local patch, which is how manifolds are described, a local patch is always orientable. So you shouldn't be too disturbed that your lab seems to be orientable. It's only when you extend to non-trivial regions that it's even possible for it to the orientable to be questionable. Yeah. A flat space can be non-orientable. The mathematical term is a flat tori. As I was saying before, it's largely unrelated to curvature. I'm not sure that these are physically interesting, these flat ones, but it's just for anyone who thinks, oh, such solutions don't exist. Well, it's trivial, they do exist. Yeah. And what it means is, so how do you know it's non-oriented? Well, it's not possible to define a global space-time coordinate system consistently. So your X, your Y, your Z, and your T directions, you can't put that coordinate system, those 4 unit vectors or whatever, and smoothly apply them in over the entire surface. You will get entire space, I should say. Somewhere you will get contradiction. Yeah. And for it even to be possible, the space-time must have non-trivial curves, something like those wormholes, some curve that's not trivial, that can't be contracted. And if it's non-orientable, there will be some paths, and these will be ones going around non-trivial curves, where the orientation changes. So if you send a left-handed object around the path, it will appear as it comes back to come back right-handed. If you followed the path through as an observer, you would think your orientation hadn't changed, and then an external observer would think it had changed. And the same with time.
Excuse me, I have a little confusions. So this number 4, it's referred to the general covariance in general relativity. It's related to that, or it's not possible to define a global space-time coordinate. For example, we have a anti-de Sitter space-time. So this space-time has a global coordinate representation. So does it mean that this space-time is non-orientable, or there is any relation between the, for example, global representation of the spatial of type of the space-time with negative curvature and orientability, or not? Or maybe I am not right. I don't know. Just is it anything related to the? I mean, if we find the solution for Einstein equations, for example, anti-de Sitter solutions, and this solution is a solution hyperbolic space with negative curvature, and then possibly we have a global coordinate representation for the metric. So does it mean that the space-time is orientable or not? I mean, Because I see you say that this is correct. You say
no, you're
topology
you're asking a sensible question, and I wish I had a more fluid answer to it. Usually in general relativity with the curved surfaces and non-trivial topology, it is generally at the very least difficult to put a single coordinate system around the entire space. It would be normal to do it with patches, and indeed with the Schwarzschild solution, that was one of the puzzles for quite a while, the fact that you have a coordinate system and it starts going wrong somewhere. It took a while to realize you actually need to patch it in with another one, or then maybe you can find some very strange coordinate systems that actually work through the whole region. I'm trying to, there's a slight complication here, and it comes about with the even with the Schwarzschild solution. That you can do that with 2 mouths of a wormhole with, I think, a single coordinate system. I think there may be some changes of sign as you go around it. But what I would think, what I'm definitely saying is you can't produce a tetrad of unit vectors and smoothly define them all the way around. In the Schwarzschild solution, for example, the R coordinate changes from a space coordinate to a time coordinate, and then back again if you come out the other wormhole.
I think your interest is in the, as I understood, is wormholes. So in the case of wormholes, yes, I understand. Because my question was about non-vacuum solutions, like when you have a cosmological constant, so then the curvature tends to negative, and that's all. So I understood that you're talking mainly about the wormholes, and yeah. So
well,
so this is about
I'm intending on this slide to be making true statements about orientability, regardless of any surface. I believe that these are all true. I am not sure how to interpret this in terms of, I've not studied the de Sitter one. I don't know how the coordinate system is set on them, so I can't answer all that well. But this,
thank you very, thank you very much.
Yeah, okay. The one thing I would be clear on this is perhaps to say it's not possible to find global space and global time coordinate systems. I've got to say you can't just have a coordinate that's flipping between time and space, and that it may well be a counterexample. Yeah, so if it is non-orientable, so that I mean this is one of those conditions that's hard to prove that you haven't done it, isn't it? Whereas the paths is the other one. If you've got these non-trivial paths, then you can go around them and plot around them and see what happens. And the Mobius strip's the famous example, and I'm going to say more about that near the end. So some examples of non-orientable surfaces. There's the Mobius strip, which is a 2-dimensional surface. And it's a nice one because you can embed it in 3 space, so it's easy. You can actually make a model of it. And wormholes, Einstein, Rosenbridge are some examples. So there's your Mobius strip. You've got just an S1, a circle, but the orthogonal direction, if you were trying to decide which was up and did that all the way along, deciding, oh, this is up, this way's up, this way's up, you get back down to the beginning and you'd be contradicting yourself. You can't consistently put a direction, the opposite direction. You can put a consistent direction all the way around the red. You can go around this quietly. There's no problem at all with that. It should be obvious. And this is an intrinsic property. You don't need to be outside the Mobius strip to do this. It's a property that can be defined within the surface. And the geometric models of particles. depends how you define this throat. This is very much how physicists would draw this. I mean, I don't know, you know, the mathematicians would draw this by taking, in this case, R2. They would cut a ball out of it, disc out of it, another disc out of it, and then they'd say this point is the same as this point is the same as this point. So they just do it by identification of points, and the physicists draw it the same thing this way. But in principle, this can have every combination of orientability. I don't know if you can see it. This is the orientable one, yeah? So this point here is identified with this point here, and this one with this one. But if the identification flipped around so that this one was identified with that, and this side went to that side and so on, you'd have something that in some dimensions would be not be orientable. You have to watch the number of dimensions, of course, to get it, because if you flip the X and the Y, then you flip two coordinates, and it's the same orientation again. But equally, when you join these up, you could join them up with the time direction flip so that it changes, just like, well, the Mobius strip, you'll usually make that, won't you? You take a strip and you'll join it together with a twist. You can do the same with this, with space, and in principle, if you could do it with a time direction. And in this example, although it talked about as two black holes, I think if you look at the mass, what you'll find is the R direction becomes a time-like vector, which goes inwards, then starts coming outwards. So what's this person's inward time direction becomes this person's outward time direction. And my understanding is that this is non-orientable, non-time orientable. There's some issue about what you need at the throat to make it traversable. So it's the picture makes it look better defined than it really is. Going back to the Mobius strip, we generally take this as a two-dimensional space-like surface that's not orientable. You could review it as a space-time diagram. Here's our one-dimensional space, S1, and we could say that the time it's evolved, things are evolving on it. You could imagine a particle moving along it, and you could draw its trajectory on here. Yeah, is that making sense? No one brave enough to speak for everyone else. You can tell, can't you, if you can see everyone going blank? But I can't. So you could regard this as a space-time diagram, in which case it's a space-time diagram for a non-orientable, not a space-time that is not time-orientable. And there's some nice consequences come out of this. They're nice mathematically and physically, and they've resulted in published papers. So that's nice for me. So you can show how I did this pictorially, didn't I? Showing the flux going in and out of the wormholes, but you can do that in really quite a formal way, which is what we tried to do. And Tamodima was a mathematician, so he did it in every dimension and everything all at once. These models explain spin half, things that have the transformation properties of spin half. Which I think is needed explaining. No, a lot of people don't seem terribly bothered about that. I mean, I could say more about it later. And there's a nice paper on the orientability of space-time, which tells us how we can test for this, which gives a very surprising result. So this is the flux through the wormhole thing. What comes next? So you can see mathematically what's happening. The flux is measured by the Faraday tensor. So that's the time coordinate. That's the XX, YY, ZZ coordinate component, rather. So these are the electric fields is the space-time component. So if the time changes, then basically each of these changes, but the B fields don't change. And I don't know if you're interested in this, it's in the slides. This is the detail of it. You can work it out quite formally by, if you define charge, well, it is how we define charge, isn't it? We do a surface integral of the flux coming out of a region, and we use What's-its theorem, Stokes' theorem, to then reach some conclusion about the charge inside that region. Or we could define the charge inside and then work out the flux afterwards, yeah? And
also Maxwell equations you can write like this. So what's the
pardon?
difference?
What?
You can also write Maxwell equations with these equations.
Yes,
Maxwell
that's right.
equations. What's the difference? The difference, of course, is probably space-time.
Well, the point is that this derivation assumes, makes an orientability assumption. And if the orientability assumption is not true, then there are counterexamples. So this relationship between the surface integral and the volume integral is only true if the space is orientable. Otherwise, there are some counterexamples. And if, yeah.
Okay, so you say Q is 0. What? No, equal 0 means the line 4.
Right. If you have the source-free equations, so d star f equals 0, yes, then this proves that the charge in a region is 0. But it does it because if you look at the flux coming out of the surface is equal to the volume integral of d star f. If d star f is 0, like no sources, then you will conclude that Q was 0. But this step here is not valid for a non-orientable space. You can have Q being non-zero, even though this is 0. Which is only saying mathematically what you saw in the little picture of the flux disappearing down the wormhole. And there's an analogous result on for the magnetic flux. And the magnetic flux, because let's see, this fails because of orientability, but you can change it to the divergence theorem rather than Stokes' theorem. But that requires that the free volume is co-orientable, which means that there's a consistent normal to the space, and that fails in the magnetic case. So no, 3 and 3 is right, because the star operator is not well defined if it's not orientable. Right, spin half. Does that puzzle people or not? I mean, well, what's happening if you consider like a neutron? We know that if we turn it around 306 degrees, that's not an identity operation. Now, I know the maths and the spinors and the quantum theory all works. There's no contradiction here, but how can it be that you rotate something around 360 degrees and you're in a different state? And don't forget that rotation could be the neutron not moving, you just smoothly changing your coordinate system around. And if anything is an object in R4 or an object in R3, you can give it values, properties, densities, field strengths, whatever, at every point. And if you turn your coordinate system around 360 degrees, you'll be back to an identity. Experimentally, we know that's not the case for neutrons or any spinor, and we need a different mathematical object to represent it. So there's no problem with the maths, but there's a real puzzle about why 360-degree rotation isn't an identity operation. I mean, what's happening, of course, in all the particles, if the particle has the symmetry of a scalar, it's perfectly symmetrical, then you represent it with a scalar field. And if something is like has the symmetry or properties of a pencil, you represent it with a vector field and so on, yeah. And then
Well,
But
can I add something to that?
yes.
When you rotate a spinner by 360 degrees, all of the real valued properties that you calculated from it are not changed.
Yeah,
absolutely. The only thing that's changed is your representation of it. And I see it as no different from going from a positive square root to a negative square root. When you square it, you still get the same answer.
Okay, but you can do interference experiments where you interfere the left-hand beam with the right-hand beam, and you can tell whether that neutron has been rotated 360 degrees or 720 degrees. So there is a physical difference between how that neutron's been rotated down the one axis.
I think there's an interference because you have the two spinners, and yes, they are.
Yeah, but I mean,
you can see the relative phase and so forth.
Oh yeah, no, sure. I mean, the maths all works, doesn't it? And there is a relative phase, but you can experimentally tell whether the neutron going down the right-hand side has been rotated 360 degrees or 720 degrees. They're not identical. They give different results on the screen. And that's why we use the spinner representation. And then, as you say, it's just the phase. And thank goodness, if you're just looking at things in isolation, everything is sort of well behaved, because that's true, isn't it? Generally in quantum theory, that the phase is not a directly observable quantity. Yeah, that's so even for a scalar.
All right, go ahead.
Yeah. But if we're modeling geometric particles, how does that going to transform under a rotation? And I did a paper with loads of representation rotations. Basically, what this, how many pages does this go on for? Far too many. Right. I'll leave this up. I'll go through this slowly for those who want to read it, and I'll just waffle. Basically what this is about is, so imagine you got something like a wormhole, some complicated topology, you don't really know what it is, but you can rotate if it's a particle model, it's asymptotically flat. And we've got a sort of lab frame that it approximates to. We can do a rotation in that lab frame. We can rotate everything around 360 degrees. Question is, can we extend that in through the entire model or not? Can we describe a rotation field everywhere? And if we can, then effectively we can rotate the entire object a 360 degree rotation, and we'll be back where we are. If we can't extend that rotation vector field in that operation, then it can give some interesting properties. And there are three spaces that have been known that you cannot do this to. Something where you take out a cube out of a three space and you join together the opposite sides but do a 90-degree rotation, then that you can't extend the vector field through that. You can't extend a rotation into that object, right? But what I was doing was, so mathematicians can talk about this, but we're physicists, yeah? When we're doing a rotation, it's parameterized by time. We start with one angle at one time, and a bit later on, we've rotated round and the time's moved on, yeah? So if we can extend a rotation transformation through an entire region so that it goes from 0 degrees to 5 degrees and so on as time moves on, then that actually defines a time direction everywhere. So if you're not time orientable, you can't do that. You can't necessarily do that. There may be some symmetries that make things equivalent, but in principle, you can't do that because it would define a time direction everywhere. So these time non-orientable objects, structures, will intrinsically have the rotation properties of a spinner. There'll be a part that's effectively anchored that cannot be, the only way you can consistently do a rotation is to have a stationary part of codimension 1 that doesn't move, yeah? And there are some lovely examples of this. So it's like these, and if you come across one of these, got some little videos that we'll play shortly. They work when you try and rotate an object where one bit's like nailed to the ground and you're rotating the other end of it. And that has the rotation properties of a spinner. The point that people don't seem terribly bothered about generally is what on earth is tethering a neutron and stopping it turning around? Well, I'm telling you what it is, that somewhere is time orientable and the causal structure is preventing that happening. So do we have some examples here? Have you seen these demos? Yeah, then which one do you like the best then? I got the belt one. This is the most scientific one, but is visually less I didn't manage to extract this. It's you're looking at it here, but this is done by a mathematician. So this is showing the spinner state and the path this is taking through SO3, because this is to do with the fact that the space of the rotations, SO3 is not simply connected. So I don't know if I'm capable of pausing this.
So if this is the www link, then it opens a different window. So we will not see it here.
So that
you
again?
need to switch to the window.
Ah, right. Sorry. Yeah, I've got my telly connected to my computer as well, so I think I can see what you can see, which is my slide saying belt demo and arm twisting demo. On my computer, I've opened up the web browser. And new share. Right, yep. Sorry, I'm obviously an amateur at this. Is this any better? Yeah, are you seeing this page of my web browser now?
Yes.
All right, okay. Yeah. So here's the belt. It's at 0 degrees, and this end's tethered. Yeah. So you're rotating this end. You can't extend the rotation all the way down the thing. I mean, because this end's tethered, and therefore, let's see if I can catch it. There we go. I think my chance of pausing it at just the right time are a bit slim, but I don't know. Anyway, I'll let it just play itself out. Yeah. So this end is staying fixed, this end is staying fixed, and after 720 degrees, you can effectively untangle it. Right. Okay, I have some of these. Right. He might talk to you if we're lucky.
90 degrees, 180 degrees, 270 degrees, 360 degrees, 450 degrees, 540 degrees, 630 degrees, and 720 degrees. Wonderful.
That's a cheap demo, isn't it? My yoga teacher did this in one of the exercise classes, and yeah. So I didn't realise she was a physicist. She didn't realise, but she does now. So in this part, the elbow's tethered, of course. So, sorry, the shoulder's tethered, and you can carry on doing it. Yeah, you can do it with a tray with drinks on and do it as well. And this is one of the clearest ones. And then I look
2 pi around an axis, and that its rotations of 4 pi that correspond to the identity comes from a mathematical property which can be seen in other systems. This appears in particular if one performs rotations of parts of the deformable solid body with respect to one another. The most spectacular example is presumably how the dancers of Bali twist their arms as they dance. But let's concentrate on this rhythm on the stick. I will perform rotations of the lower part, which is materialized by this stick and this piece of cardboard. First of all, I claim that a simple translation of the solid, or the part of the solid, with respect to the rest, is equivalent to the identity. Now let's make a rotation of 2 pi, 2 pi, and I try to untwist this by a translation. And whatever I do, the rhythm remains twisted. So now let's try a rotation of 4 pi. I start in this initial position. I do pi, 2 pi, 3 pi, and 4 pi. I made the same translation as before. Now, at this point, the system looks quite entangled and twisted, but nevertheless, the combination of all these operations is indeed equivalent to the identity.
Right, I will. Ooh. I'm trying to put my.
So, may I shortly give a comment?
Oh yeah, please do. Yes, yes.
Yes. So everybody which is connected with his surrounding feels 4 pi rotations.
Yes.
Everybody which is connected. A disconnected body feels only 2 pi rotations. It comes back after 2 pi. And the body which is connected to the surrounding comes back only after 4 pi.
Yeah.
If I can share my screen for a moment, I can show it with the Mathematica.
Yeah, no, I've seen the ones. I've even worked on them as.
Can I share?
I don't think it's a trivial. It strikes me that it needs explaining because it isn't just you can do these rotations either by rotating the object or just rotating the coordinate system, and there's something is happening with a spinner that means that effectively it's tethered like in those pictures. So I'm struggling to resume my slideshow. Are you seeing a slideshow? Are you seeing its full? What are you seeing on your screens?
We see.
Yes. Spin half. 26 slide.
Are you seeing that list of 3 different videos?
Yes, we see it.
Yes. Okay. Sorry guys.
What is the problem?
I'm trying to get. All right. Yeah, it's not displaying on my. That's it. Okay, I'm back where I was before now. Right. What I wanted to show you now was, it's often been said that it's an experimental decision, an experimental thing to decide whether space and time are orientable or not. There are some arguments given that it must be orientable, but most of that is based on the fact that, as I said before, if you take any limited region, then it will always be orientable. And it's only if you try and extend whatever you're doing, your coordinate system right through the manifold, that it becomes relevant. So, for example, there's a problem, you can't put spinor fields on manifolds that are not orientable. But that's not really relevant here. My view of a spinor field describes the probabilities of finding a spinor object somewhere. You wouldn't expend that field into the interior of the object itself. So I'm going to show you how, as an experimentalist, we will test for space and time orientability and come up with an obvious answer. So what I'm trying to show here is some region of space, and we're curious about whether it's orientable or not. So we start off in the lab with our reference frame coordinate system. That's supposed to be an X, a Y, and a Z. And there's two of these. One of them stays in the lab and is our reference point. And the other one sends on our probe, comes along here, all smoothing continuously, goes through this region, comes back out, and we do a comparison. And the mathematicians are happy with this, because here I've done a closed curve, and I either will or will not have consistently put an orientation around this curve. If this agrees with this, or when it comes out, then everything's just fine. If this region is not orientable, space orientable we're talking about, then if you stayed with this probe, you would be right-handed all the way through. You would still be sure that you were right-handed. But when you compared with the lab frame, the lab people would think you were left-handed. You would think the lab people were left-handed when you came back. And you just couldn't do it consistently. So that's how you would decide if region R was orientable or not. So a right-handed person would go in there and they would come out feeling just the same as when they went in, and everyone else would think they were then left-handed. And the same with screws, left-handed threads will turn to right-handed threads and so on to an observer, but no one will have thought their threads had changed, and no one will be able to decide who's the right or wrong. So we might try and do the same thing for time orientability. And here's a false test of time orientability. I've let the cat out of the bag here by telling you it's false. So we're doing the same thing, but now our thing that defines time orientation is a clock. So we have a clock ticking. These are supposed to have numbers in them, 1, 2, 3, 4, 5, and so on. And then we send a probe with an identical clock. We send it in the region, and you might think that then the probe comes out, you would compare it with this probe and see if it was counting backwards in time or not. But that's wrong. But this is not a test of time orientability, because if the numbers on this clock, the time direction, since the arrow of time is determined by the upward counting of these clock numbers. So if it went 1, 2, 3, 4, 5, 4, 3, counting down, then at some point it must have gone from counting up to counting down. At that point, there is no time direction, and no one's proved anything. You have not translated a forward time direction through this region and out again. A proper test of time orientability is this, which is much better because the picture's better. So here we have our lab frame with its clocks, and the lab frame can right big. I'll put the clocks over here just to help us. And we send our probe in, which must, this is the key to it, this probe must always be counting upwards in time. But it must seem to the outside observer as if it's going the other way. And that's because this is what happens. At this point, from in the lab frame, the clock is now going backwards in time. In the clock frame, the lab is now going backwards in time and they're going forwards in time. So this is what a test, this is a definitive proof of a region that is not time orientable. But hang on a minute. Look at this back in the lab frame. When you start the experiment, you start the experiment at time equals 1. You have your probe going in here. But hang on a minute. You now have a backwards counting probe going in here as well. And if you don't have this backward counting probe here at time 1, you can't consistently do this experiment. So what does this look like in the lab frame? It looks like a clock going into this region. I will jump ahead here and say I'm calling this an anti-clock because this is a backwards counting clock that goes into the region as well. And the two disappear. There are no clocks later on to the lab observer. If you stayed with the clock, you were a clock and you're still a clock. So a definitive test of time non-orientability would look exactly like a particle and an antiparticle going in and annihilating each other. So what do we conclude from that? Well, you could say that space-time is not time orientable and that particle-antiparticle annihilation events are evidence of that. That's what I would say. We have just proved that time is not orientable. We could say that these are indistinguishable phenomena, time orientable and particle-antiparticle annihilation. Yeah, they're alternative descriptions of the same phenomena, which I'm okay with. You could say that time orientability is untestable, which is interesting because to the mathematicians, there's just no problem with defining time orientability. But you saw that experiment and now you'd have to try and construct it and what it would look like. You could just conclude that it was untestable. Or you could say...
May I ask a question?
Yes.
In your earlier slide, the slide before.
Yes.
If you have particle antiparticle, then you have afterwards you get 2 photons, so some energy is left. So, but in the case of your clock, you didn't speak that some energy is surviving.
No, that's right. That's a very interesting question. That is going to be one of my future research topics. Is what happens if you try and do an energy analysis of this? Yeah. This says nothing about the energy, does it? Yeah, you got a particle, you got an antiparticle, and it's just vacuous here. Yeah, yeah. No, absolutely. It's just the question I add to it. Yeah, where's all the energy gone? Yeah. So, well, you could say it's not an objective property of space-time because the outcome of the test depends on the observer and how you're setting it up. It depended on the. You think you're doing an experiment, but it must depend on how you're setting stuff up here. And how you're setting stuff up here must depend on whether you actually encounter the night. If you didn't encounter this region, this clock couldn't be counting backwards. So the state you've got here will depend on what's happening at point 4 here. So this is sort of interesting. The one thing you can't say actually is you can't say that time could be orientable. You've either got to say this is evidence of non-orientability, or you can say it's untestable. But this is how you would test it, and it happens. So So yeah, really. So that's sort of interesting, I thought. Anyway, so I think general relativity may be the unifying theory after all. And so what I would like, yeah. So what I'm been saying here is general relativity is a classical theory. We have classical waves or classical phenomena, but there are some special cases. Whenever when you have acausal structures, time reversing structures, they obey quantum mechanics rules. And that's what I'm working on. I'm carrying on working on that. So going forward, this is sort of inspired by the Mobius strip thing, which most stuff is because it's the only one I can imagine. You can analyze the orientability intrinsically on the surface of the Mobius strip, but actually you can make one, stand back and look at it, and what is happening. If this Mobius strip here as a space-time, yeah, you'd be saying, well, actually the time direction in my free space, the time direction is twisting as it goes round. And you can stretch the Mobius strip out. It could be flat in some places and not twisting, but it's not trivial. Over the entire circle of the Mobius strip, it must twist through pi. Yeah? So you can actually use this twisting of the time direction to define a U1 bundle, an angle. At every point on that Mobius strip, it's at an angle to what it was before. And the accumulation of that, the integral of that is non-zero, non-trivial. Yeah, which effectively means you're defining a U1 bundle, like a compactified Kaluza-Klein theory, where you can derive electromagnetism from that, as they do. I mean, with some sort of caveats or puzzles or bits that are not quite dealt with properly, but basically this gives an origin for electromagnetism. What Kaluza-Klein didn't say is why we have this U1 bundle, but I'm telling you why now, that we have a time direction, it's twisting around. And this is, I've done a paper on this, where I start with the twisting of the time direction, define the U1 bundle, and get the equations of electromagnetism out with some slight puzzle about what's happening with the charges. And the thing that I'm working on now is, can we take this forward and somehow get something that looks like the pilot wave? Because, yeah, so that's what I'm looking at now. I've now finished my talk, and you may ask any further questions if you have any. I'll let you ask some questions as we run along, didn't I? So, yeah.
Hello. So thank you very much. So please everybody to unmute and we can discuss. So I personally have also realized this hypothetical possibility of non-orientable wormholes, for example, 10 years ago, and this is very nice discussion for thermodynamics, that you have a rocket going through such wormhole, and then from our perspective, the thermodynamics works in opposite direction inside such a rocket. For example, if
there's a lot of parallels between obviously time travel comes up in science fiction, and obviously one answer to the consistency issue is often parallel universes, isn't it? Which you can see why, which it obviously comes up in a separate way in quantum theory, and it's a way of trying to get some sort of consistency. I mean, some people talk of an inconsistent solution or a paradox. Well, if you solve your equations and they don't agree, it's not a paradox. Yeah, wrong. I mean, it's not a solution, is it? So, but it's like there's something constraining the possible outcomes. And what I'm saying to you is, it is quantum theory gives you those constraints.
So I don't think there is it is self-contradictory. In contrast, I think it shows how to understand time in this eternalism block universe way, that we have a solved four-dimensional situation and we just travel through it through time. This is the proper way to see time.
Yes, though block, you tend to think of something that's sort of very well ordered, whereas this very much isn't. But I think you're right. You can't. This is certainly contrary to is this idea that you can have a space-like hypersurface and things just evolve. That is quite contrary to this. This is not how the equations will work, and you cannot do that generally. Yeah,
we have one four-dimensional solution, and we just travel through it. This is the proper way of thinking about physics. So.
Yeah.
I have a question about this idea of the phase rotating because of time is changing direction.
Yes.
So if you have the phase of a wave, let's say cosine of kx minus omega t.
Can I pause you a minute?
Okay.
Oops. I'm not seeing all the participants.
So there is this button.
Oh, yeah.
Yes, so we had the discussion about this spin 1/1/2. So about I've shown you that we can have these topological singularities with spin 1/2 if using a not vector field with arrowheads, but saying that this and this arrow is the same. In this way, rotating by pi, then you get the same configurations. So it has the same behavior.
So someone else was asking a question, wasn't they? So I didn't catch who it is.
Yeah,
I'm not seeing your picture, but I can hear you very clearly.
Okay, well, I'm not on video, but
oh, that's why then. Okay.
My question is, if you're looking at the phase and you're saying the phase is changing because the time direction is, I guess, twisting.
Yes.
But if you're looking at the phase of a wave, let's say cosine of kx minus omega t,
yes.
You could just as well change the phase by changing the direction of the wave vector k as by changing the time direction. The important thing is the relative sign between the kx and the omega t. So changing the sign of the k would have the same effect as changing the sign of the t in terms of the propagation of the wave. Is this really different? Is it really different than just having the wave go back and forth as opposed to time going plus and minus? So.
I know what you're saying, and it is quite interesting when I do some equations and I think, oh, I've got to add in a thing going back in time. Well, actually, it's just traveling from the opposite direction, isn't it? No, what I'm saying is, I'm not talking. There's no wave here. What I'm saying is the time axis points in a certain direction at one place. It points in another direction somewhere else. If we're doing that Mobius strip, if we integrate how it's changing around the entire Mobius, it must come to an odd multiple of pi. But at any point, it will make an angle with some reference position. So yeah.
Maybe regarding the spin, maybe let me share this picture of this. Okay, so just that's one slide. So we had this discussion through emails. So I'm saying that this is spin 1/2 also in the same definition. So the definition, I think that so there's one definition that quantum rotation operate on that if you have spin s particle and you rotate it by some angle, then the quantum phase rotates by angle times the spin. So this is the kind of basic definition, and this 1/2 agrees with this definition.
Okay, yeah, this wasn't what I was expecting when you said about Mathematica. I was thinking of the models that have been made of the ropes and stuff. Yeah. So what you're talking about here is about the transformation properties of the vector field.
Yeah, so I'm saying that instead of vector field, I take the direction field, that this and this is the same.
Yeah, okay. Yeah.
Well, just to add to that, it's pretty straightforward to take the second order wave equation and basically factor it into a Dirac equation.
Yes.
So there's a very clear association between spin half and wave propagation. And in real space,
hang on.
The meaning of spin half in the real valued quantities, the real valued things that you calculate, like the actual spin.
Yes.
The really, I guess, I don't know if you want to call it topological feature or whatever, but the physical feature that you see in real space is that you have independent states that are 180 degrees apart.
Yes.
And for example, that would be waves propagating in the plus X direction and the minus X direction. Those are independent states and they're 180 degrees apart. And the only way you can describe those in a first order equation is using spinners.
Yeah, sure.
So yeah, so a lot of these things that people attribute to, I guess, quantum mechanics or whatever, just seem like ordinary wave properties, actually.
Yeah, well, I'm with you on how there's no problem with how the maths works out. It's just why that's relevant to describing some of the particles in nature. And it is a quantum mechanical thing. There are not classical free particles that objects that will need that sort of description.
Well, there are classical particle-like waves, or I guess they call them breather waves, or with the sine-Gordon solutions. So they have very much particle-like behavior.
Yes, and then you say they've got spinor transformation properties.
Yes.
Okay, I might be interested in looking at a link on that.
Yeah, I put one in the chat that I'm working on now. So.
Okay, thank you very much.
I did not understand yet. Where do you think that these wormholes could be realized? In universe or in elementary particles?
No, very much. This is a model of an elementary particle. Yeah, an elementary particle is a small region with non-trivial topology and non-trivial causal structure. So, for example, in the EPR experiment, there is actually causal links between the two arms because the particle has traveled there from its source.
On the first statement, I would agree. On the second statement, so I have opposite, different opinion.
Yeah.
Yes, this is
moment, Jarek. What would happen if you send a photon through this wormhole? Wouldn't it change orientability, or wouldn't it change from right-handed to left-handed?
Well, if it was, well, yeah, I don't know. It depends on your wave solution and which orientability it was. But it's straightforward to calculate, isn't it? I think.
But I would assume that it's going from right-handed to left-handed.
Yeah. Well,
because if you are saying that the screw is changing the orientation. So
the thing that I'm interested in is the time orientation changing. I think in some of those models, time and space orientation both change at the same time, which is a complication.
But the electric field vector in a photon in the conventional theory.
Yeah, so the electric field would go to minus itself. Yeah. And the magnetic field would
right-handed to left-handed, and does not. Does not agree with the experiment. So if you send a photon through an electron, it should change orientation.
Yeah, okay, that's interesting. I've not looked at that. I've not looked at that.
Yeah, please think about it.
Yeah,
so in many statements, I agree with you. So in the picture, that the gravitation is closer to nature than elementary particle theory in the moment.
Yeah.
But of course, I prefer a different model.
Yeah.
So I can describe charges with rotations of space of Dreibein in space. That's sufficient.
Yeah, so there's missing this charge quantization that the Gauss law can only give the integer charges. I haven't seen it in your slides.
Yeah. So and, in this model, I get charge quantization, and
Yes,
I get also spin quantization.
So we need to repair the Gauss law. That it cannot only give any real charge, but only integer charges. And Manfred does it with using Gauss-Bonnet theorem. That makes that Gauss law integrates curvature of the field, and it integrates to integer topological charge. So it was missing.
All right, you're distorting quite a bit. I'm struggling a bit there, but.
So I'm just saying that what is required in this charge quantization to repair the Gauss law, that it can only give integer charges, and it can be
The
done.
interesting thing about the quantization, the Kaluza-Klein, the U1 bundle approach to electromagnetism, it does naturally give a quantized charge, and that charge is monopole charge, but it's not clear to me that magnetic and electric fields that we've labeled are the same as though it naturally pop up in the Kaluza-Klein theory. I think people identify them first, then look at the physics and get a bit puzzled about the magnetic monopoles. They could almost do the opposite and say, look at what Kaluza-Klein's saying, and then compare it and think, well, we've got D and B fields the wrong way around here. I don't think it's quite that simple, but that's something I'm looking at now as well.
But magnetic monopoles were not found, so we don't need to think about magnetic monopoles.
Yeah, so Manfred repairs it by using a dual field. You get this F tensor you have shown, and replace magnetic and electric field, and instead you get electric monopoles, that is charge. You don't get magnetic monopoles, only electric monopoles, as it should be. So this is a very good idea to use the dual Faraday tensor instead of the original one.
And there's another interesting thing that I'm looking at is the Kaluza-Klein stuff. It comes out with two. Well, it starts as Kaluza-Klein. The motivation is we're extending general relativity to fifth dimension, but then only really what starts giving something interesting when they then start adding these extra conditions in. So that was probably the wrong place to start. The right place to start is to say, we've got space-time, but there's some additional structure. There's a phase everywhere. What are the equations? And then it comes up with two remarkable equations. It comes up with the source, an effective source from the electromagnetic stress energy tensor. It gives the right form for that. And it gives the Maxwell's equation, source free, and it gives the equations of motion. But then what's often glossed over is it actually gives one or two other equations which don't seem to make a lot of sense, and it seems a bit wrong to praise some of the equations without and just be dismissive of others. And of course, if it's predicting any charges at all, it's magnetic ones. But then that's a bit of a puzzle because the equation it gives for the force law is the equation we're familiar with, which is for an electric charge moving in a field, whereas it actually predicts magnetic charges, which is quite strange. And you couldn't write down, I mean, imagine the monopole equations that come out from Kaluza-Klein. It does, locally, it always satisfied df equals naught. So you would always still have div b equals naught, but still have monopoles. So if you wanted to step back from the monopoles and try and treat them as a charge density, you have a real puzzle doing that with the identification that's usually done with the A fields and the B fields and the E fields. Sorry, that rambled a bit.
I have a question about general relativity.
Yes.
It's puzzled me for a while. One of the predictions of general relativity is that if you go from place to place, you get a varying speed of light. You know, if you're, for example, near a massive object, the speed of light is slower, and if you get farther away, then it's faster. And so my question is, can't you work backwards and just say that all of gravity is just interpreted as the change of speed of light when you're near massive objects? Wouldn't you be able to derive all of general relativity just from that assumption?
I don't think it's quite saying that. I think the speed of light to an inertial observer is the same for everyone, isn't it? I think you're just doing the translation between different coordinate systems and saying in one coordinate system it looks slower.
Yes, the person who's there can only, it always measures the same speed, but if you compare, like if we look at from the Earth, you look past the sun, we see that there's a speed of light appears to be slower.
So an observer in an asymptotic reference frame would see the speed being different. Yeah, sure. Yeah, I don't know quite what that gives. One thing that's not talked about all that much, I don't know how many people realise it. There's a Schwarzschild radius at r equals 2m, beyond which nothing will come out. But there's a radius r equals 3m, which is also interesting, because that's the radius that the speed of light will go around in a circle. And the speed of, if you have a lot of light at r equals 3m, then it's actually a source of energy in itself.
Could you repeat, please, what is with the r equals 3?
Well, that's the orbital radius of a light ray.
Okay,
Yeah, people don't always know that, do they?
So it stays on this radius because.
Yeah, I think it's an unstable one, but it stays on it.
Okay, so it's a station. It's maximal, so maximum, extremum state, so to say.
Yes,
it's not stable,
that's right. Yeah,
unstable.
it's an extremal orbit. Yeah.
Well, that gets at what I was asking about, which is if you can just think of gravity as refraction, that the light is always bending toward the slower speed.
Yeah.
And there are some papers on that, but I think, as far as I know, they only deal with weak gravity. I don't think anyone's solved the full equations that way.
Yeah, you are right. It's the consequence of gravitation that speed of light is changing.
Yes,
Not
yes.
the inertial observer. For the inertial observer, it's constant.
There are certainly solutions of gravity or approaches to it where you split out the high frequency components from the low frequency ones, and then treat the high frequency ones, there's like gravity waves, this is really, I suppose, as being a source of space-time curvature on a larger scale, which I think has some similarities to what you're saying, but isn't quite the same.
But you need also that the speed of time is different in different gravity fields.
I think
it's not enough only to change the velocity of light. So if you have drops in different heights of Earth, they are running with different speed.
Yes, I think this is what Robert was talking that we have the refraction, we have change of speed of light, and so it also, I think, leads to the time dilation. That locally the atoms are built a bit of electrons, protons, so the speed of light changes the speed of the processes inside. So I think the change of speed of light also changes the speed of processes inside given. Because they are all governed with electromagnetic exchange.
Yeah, but you need both. Speed of time is changed, and also distances are changed. And of course, altogether is, of course, change of speed of light. So I think it's the same. If you say it's speed of light, or space and time is changing. Length and time speed is changing. I think that's the same, because we measure space with velocity of light. In the International Measure System, we define c, and we measure meters with speed, with time.
Yes, so I think it's difficult to distinguish if you are talking about time dilation or space contraction because of that.
Well, I didn't understand.
So I'm saying that it's difficult to distinguish if it's just time dilation or also space contraction due to general relativity effects.
I think you have both in special relativity. You have both also.
Yes, yes. Special. There are no doubts about special, but what about the general?
Yeah, but I think they are related because of the elevator example of Einstein. So it's the same if you are using a particle which, if you are moving in a system which has velocity and yeah, I think they're related. There's effects in special relativity and gravitation.
Yes, I agree. And actually, there's engineers are making artificial black holes with just optical trapping of the light using refraction.
Well,
And
a
I mean,
model of a black hole.
it's not clear to me that there's a real difference there. So.
No?
Okay, I think I'm going to say goodbye now. Thank you very much for inviting me.
Okay, thank you.
You're welcome.
Yes, thank you. Nice talk.
Have a nice day. Thanks.
Bye. Thank you.
Thanks.